Hi everyone, in this video I wanted to show you how you can modulate a transmission line. I'm gonna be using the content of the book Transmission Line Design Handbook by Brian C. Waldo. Transmission Line Handbook by Brian C. Waldo. Being more specifically, I'm gonna present the model of the figure 2.1.1 of the page 10. This model can represent both a coaxial cable or a microstrip line. Basically, we can represent these structures in terms of RLC elements in the network. Of course, in today's days, we have softwares where we can simulate it, but if you are persuading a profile as hard engineer, so it's essential for you to understand deeply about this topic since PCBs are made up basically of dielectric and microstrip wires. Now let's draw the model. It consists of an inductor in series with a resist element, and this in parallel with a capacitor and a resistor which represents the conductance of this structure, which of course is a transmission line, and it repeats along its way. L for inductor, R for the resistor, C for the capacitor, and G for conductance. We have the voltage V in and the voltage V out. And is a structure which repeats along his way. Without exceptions, in a piece of coaxial cable or microstrip line, we must consider the inductance, the resistance, the capacitance, and their conductance, since we are modulating these structures based on the electromagnetic fields which spreads or are contained all over the dielectric, and we make use of his for displacement current, conductive current by controlling the width and the length of this structure. In this model, L and R in series are described by the ratio of the rate of change is described by the ratio of the rate of change of the potential with respective y, which is the smallest piece of structure as you wish. And I forgot to draw right here, which we call it delta y, and the total length is I. And as we were saying, L and R in series are described by the ratio of the rate of change of the potential with respective y, and this is given by minus I times R minus L times the ratio of the rate of change of En with respective time. The negative signal represents the position seen by the current as flow throughout the structure. Before we go along, let's remember the equations which describes these elements R, L, and C, so you can get a better understand on how this modulation were being done. For the resistor, we have V V equals R times E, which is our old known Ohm's law. For the capacitor, we now have the time as crucial variable, since is a element which it changes, which charges, and the charge given by the flux of the current, and it is described by the value of the capacitor times the ratio of change, the rate of change of the potential with respective time. And now for the inductor, we have the potential VL, which is equal to the value of the inductor times the ratio of the rate of change of the current with respect to time. And as you can see, this is what were done right here. Now let me also remember you what is conductance before we can go on. Conductance is given by G and is the reverse of the resistance. And it describes how easy a material can conduct certain amount of current, and also can be expressed in terms of the ratio of E, the current, and the voltage. Now we can continue. The other part of the net of this structure we modulate this part now we're gonna modulate in terms of equation this part of the structure. This other part is made of capacitor in parallel with resistor representing the conductance, and is modulated by the ratio of the rate of change of the current with respective y, which is equal to minus v times g minus the ratio of the rate of change of v out with respect to time times the value of the capacitor. And again, the negative signal represents the position seen by the current. And in the next part of the video, on the part 2 of the video, we're going to continue derivating these equations, so we can get the characteristic impedance of this structure. So that's it. Thank you.